Hello everyone, I'm Xiaowen Hu. I'm here to present our paper on the choice construct in the Soufflé language. This is a joint work with my colleagues in the University of Sydney, Joshua Carr, David Zhao, Abdul Zerika, Xi Wu, and my supervisor Bernhard Schultz. First, let me give you a little bit background on Soufflé. Soufflé is a highly efficient logic engine that has been used in many specific domains. Some of the examples are program analysis in Java and TensorFlow. This is with tools like dup and PySeer. Security analysis in external virtual machine with GigaHost and Stratified, and network analysis in Amazon Web Service with Tyros. Datalog is a domain-specific language for analysis problems. Soufflé is a Datalog engine that has the extensions beyond standard Datalog, such as type system, records, abstract data type, components, functors, and aggregates. It aims to provide easy-to-use while efficient way for user to evaluate Datalog program, and it can achieve similar performance to handwritten C++ code. With functors, Soufflé is a truly complete Datalog engine. However, we found certain classes of algorithms are still hard to implement. For example, worklist algorithm is commonly found in compilers and analysis tools. A worklist algorithm typically requires a non-deterministic choice from an existing working set at each iteration of the computation. However, Datalog semantic was not built with this non-deterministic in mind, and it is extremely tedious to simulate the same effect. So in order to resolve this issue, we found in literature what is called a choice construct as an extension for standard Datalog, mainly developed in the 90s by many great researchers. The idea of choice construct is extremely simple. It enforces a functional dependency constraint on a rule, so that all elements inferred by the rule must follow the constraint. For example, a dependency with domain x, y, and codomain z ensures that x, y must uniquely define z in the element set. For example, 1, 2, 3, and 1, 2, 4, they cannot exist at the same time, since this breaks the requirement that x and y uniquely determine z. However, we find that there is no existing implementation of choice construct in modern Datalog engine, although the idea was developed a long time ago. Secondly, we found that the original design, when used by the programmer, can be error-prone, especially for large-scale Datalog program that does not commonly exist when this idea was first developed. And we think the language feature need to be improved to fit better in the modern usage. Let's consider a motivating example, a rooted spanning tree algorithm that is commonly used in program analysis. So we are given a source program and its control flow graph representation. We want to build a spanning tree from the given CFG. Let's have a look at the procedural algorithm first. So we start from worklist with only the root node. At each iteration, we choose an arbitrary node from the worklist. The set nodes includes all the visited nodes in the previous iterations. Then for each adjacent node that has not been visited yet, we include it into the resource set, and we add the neighbor into the worklist set and start the next iteration. There are two challenges to implement this algorithm in standard Datalog. The first is the action of choosing a single node from the worklist. In order to accomplish it in standard Datalog, you need to explicitly define an extra rule to sort the set with an arbitrary order, and choose either a minimum or a maximum value from the set. The second challenge is to test whether a node has been visited yet. This requires, at each iteration, to build a complement set to exclude all the visited nodes, which is very tedious and expensive. So we implement a version of this algorithm with only standard Datalog feature, resulting in 158 lines of code in Soufflé. This is obviously not the amount of the effort you want your user to put in for such a simple algorithm. Now let's have a look at how choice construct can help. On the right hand side is the implementation of the spanning tree algorithm in Soufflé, but this time with choice construct. We'll first declare an age relation with two attributes, v and u, representing the ages in the input CFG. Then similarly, we define a relation called st, representing the ages belonging in the resulting spanning tree. However, this time we enforce a choice domain on the relation with attribute u. This defines a functional dependency from u to v on relation st. Intuitively, it means that each endpoint can be added into the spanning tree only once. We then add an auxiliary tuple root L1 into the st relation, representing the starting point for our worklist. Here we assume there's a node called L1 in the graph for the sake of demonstration. Finally, we declare how to compute the relation st. The definition is really straightforward. An age vu is in the spanning tree st if there's an age ends with v in the current spanning tree, and there's an age from v to u. Finally, because of the functional dependency, node U must have not been visited yet in the spanning tree. Notice the syntax I'm using here, where the functional dependency is enforced on the relation. This is already our modified version of choice construct in Soufflé. In the literature, choice construct is defined only on the rule level. So to distinguish between different versions, we call our version relation-based choice and the version in the literature rule-based choice. There are also some pitfalls to avoid if you're using rule-based choice to implement the rooted spanning tree algorithm, but we will come back to this later. Let's first formally introduce relation-based choice. So first, a function dependency on a relation R is a set of attributes x and y belongs to R, written as x to y. X is called the domain and y is called the codomain. And the attribute in the domain must uniquely define the attribute in the codomain. And now let's have a look at the syntax in Soufflé. So A is the relation name, and each x is an attribute of A. So recall in the previous example, we have a relation with attribute u and v representing the edges of a graph. And each di, after the keyword choice domain, is a subset of the attributes, represents a domain of the functional dependency. So the codomain here is implicitly defined. So everything that is not in the domain is in the codomain. You can also define multiple constraints on a single relation, so just separate them with a comma. Finally, an example. Here we have a relation called foo with three attributes x, y, and z, and two functional dependency, z and xz. So all the elements in the relation foo must follow two functional dependency, namely z to xy and xz to y. Now let's talk about the rule-based choice developed in the prior work. The syntax and semantic is different here. Rule-based choice, as name suggests, operates only on the rule level. Here we have the example spanning tree algorithm again, and we enforce a functional dependency at the second st rule. At the end of the second rule, we write down the keyword choice, which takes two arguments. The first one is the set of attributes in the domain, and the second is the set of attributes in the codomain. Since rule-based choice only operates on rule level, only elements generated by the second rule needs to follow the functional dependency. That is, other rules can still generate tuples that breaks this dependency, and the resulting relation does not necessarily follow the functional dependency defined here. So it might seem on the first side that this rule-based choice version computes the same result as the relation-based choice version represented before. However, that is not the case. Rule 2 can still generate tuples at node L1 because our auxiliary tuple, root L1, was defined in the first rule, and as a result, is not considered by the rule-based choice constraint in the second rule. So in order to fix this, we need to explicitly add one more condition in the second rule, stating that the endpoint cannot be L1. That is a classic example of why rule-based choice can sometimes lead to programming error, especially in large-scale Datalog program, where you can easily have a dozen or even hundreds of rules to consider. Regarding the expressive power, rule-based and relation-based choice are equivalent. That is, given relation-based syntax, one can simulate rule-based choice construct, and vice versa. For example, given relation-based syntax, we can create an auxiliary relation called st prime, and use it as a bookkeeping table to enforce constraint only on the rule level. The bookkeeping table is simply defined with the same set of letters as given in the rule-based example. And the final resulting relation st just take whatever in all the bookkeeping tables. In this example, we have only one because we have only one rule with the rule-based choice constraint. This actually coincides with the implementation of rule-based choice given in the literature, where an auxiliary table was generated under the hood. Okay, now let's move on to the implementation side. Here's a figure representing the pipeline of Soufflé. For a Datalog program, Soufflé reads it in and generates an AST representation. Then it translates it into an intermediate representation called Relational Algebra Machine, or RAM. RAM is basically an imperative style representation with control flow like if and while loop, equivalent to the source Datalog program. Finally, RAM is translated into native C++ and compiled to binary. For the implementation, we've extended front-end parser. In the high-level representation AST, we added a functional dependency list for each relation and some semantic check. Finally, we embed those functional dependencies in terms of RAM operations. The key idea of our implementation is to add the existence check for insertion to enforce functional dependency. Let's consider our rooted spanning tree example again, and below is the representation used to compute this rule. The first two for loops corresponding to the two letters in the body of the rule, integrating each edge in the currently spanning tree and find an edge in the CFG such that the endpoint of A equals to the starting point of B. Then we have an if statement that enforces the function dependency. Search in the relation ST and check if there already exists a tuple that ends with B1. The button symbol here means it will match with any value. Finally, if the existence check passes, the insertion will be made. Here, the existence check is pretty cheap thanks to the highly tailored B-tree data structure Soufflé has. Notice the representation here is simplified for demonstration. During the actual implementation, we also need to handle extra auxiliary relations created for fixed point evaluation of the standard stratified Datalog, but they are mostly irrelevant with today's topic. Another thing I want to mention is that here we simply perform the existence check against the whole relation instead of creating bookkeeping table as the rule-based choice would do. Because rule-based choice cannot simply check against the whole relation, that would be semantically incorrect. It really requires a local bookkeeping table because it is only on the rule level. So on paper, relation-based choice can also be potentially faster than rule-based choice as it eliminates an intermediate table. Now let's move on to the experiment. For the experiment, we mainly want to answer the following questions. First, does choice substantially improve runtime and memory performance over equivalent non-choice Datalog programs? Second, does choice allows for easy expressivity for Datalogs requires non-determinism? Third, is there any performance difference between relation-based and rule-based choice? For each benchmark, we use three implementations: a relation-based choice, a rule-based choice simulated with relation-based construct, as presented before, and a native implementation without choice construct. Again, allow me to help you recall that the simulation of rule-based choice with relation-based choice is simply using an auxiliary relation as the bookkeeping table. This strategy coincides with the proposed implementation of rule-based choice in the literature, so their runtime cost should be the same. Also, it is technically a simulation. For the first experiment, we convert the spec CPU benchmark into a set of CFGs and run the spanning tree algorithm on it. The three implementations are similar to our previous example, so with only minor modification to fit the source data. Three findings find the result. First, with choice construct, it is much simpler to implement the rooted spanning tree algorithm. Recall that the native implementation in Soufflé resulted in 158 lines of code. However, with choice construct, it's only 3 to 5 lines of code. Second, there's no memory or performance difference between relation-based or rule-based choice. Also, like we discussed, in theory, rule-based choice has an extra auxiliary table. However, usually the number of elements follow the functional dependency are extremely small compared to the total data size. So the overhead in real-world case is negligible. The final finding is that both choice constructs are much faster than the native implementation, both memory and runtime-wise. Choice implementation usually consume a constant size of memory and can be up to 10,000 times faster in the best case. We then experimented some classic non-deterministic algorithms in related literature. Again, no performance or memory-wise difference between different choice constructs. Implementation with choice construct are usually much faster than the native implementation. And finally, relation-based choice usually result in less lines of code compared to a rule-based choice and the native version. Let's conclude this experience report. So in this work, we provide an efficient implementation of relation-based choice construct in a modern Datalog engine, Soufflé. User experience-wise, we modified rule-based choice in the literature into relation-based choice. We believe a relation-based choice is more maintainable and suitable for a large-scale Datalog program in the modern era. And relation-based choice can avoid some pitfalls for the user and usually result in less lines of code. And the two choice constructs have the same expressive power. So in case user really wants rule-based choice alien, they can simulate it without any extra cost, and of course vice versa. And finally, with either choice construct, worklist algorithm is much simpler to write and does not involve with complicated induction process or building complement set at each iteration. And finally, our experiment suggests that there's no significant performance difference between the two choice constructs. However, with choice constructs, it is usually faster than the native implementation when targeting worklist algorithms. Okay, thank you everyone for listening to this talk. I will see you in the Q&A section.